Hello and welcome to Additive Insight, the original additive manufacturing podcast and your source for news, interviews and comments on the latest 3D printing and AM intelligence, brought to you by TCT Magazine. I'm your host, Sam Davis, and today I'm joined by Hyliion CEO Thomas Healy. Hyliion is a publicly listed manufacturer of clean modular power generation systems, best known for the KARNO generator technology it acquired out of GE Aerospace in 2022. When Hyliion made that investment, it also inherited a significant metal additive manufacturing capacity that facilitated the early development of the Carno technology and is now deployed to manufacture commercial products like the Carno 200 kW Power Module. Throughout our discussion, Healy shares more on the capabilities of Carno, the company's AM workflow, and why Hyliion wouldn't have a product without additive. We also discuss how the company has scaled to a fleet of 36 metal AM systems, and how he expects Hyliion's application of the technology to evolve. If you like what you hear, don't forget to subscribe wherever you get your podcasts. You can also head over to tctmagazine.com to subscribe to the TCT membership platform and receive more additive insight via our print and digital offerings. Thomas, welcome to the Additive Insight podcast. We'll be talking today about how additive manufacturing is being used in your mission to deliver more efficient power generation technologies. But first, I was wondering whether you could take us back to the start. So Hyliion was founded over a decade ago. Can you tell us the story of how and why the company was established?
Absolutely. So this is your stereotypical startup journey of it's been a roller coaster. It's been a lot of fun, exciting, but it's come with twists and turns as well. But just to level set, we're now a company focused on power generation space for any of your viewers. So we're really using additive manufacturing to enable a really new type of power gen. So how the company started, back when I was in college at Carnegie Mellon in Pittsburgh, I had this wild idea of let's go electrify semi-trucks, bring these big 18-wheelers, move them off of diesel, move them onto electric. And that was the origin of the company. We took it public on the New York Stock Exchange in 2020 on that premise. And then fast forward to 2021, GE approached us with this really new innovative tech they had. It's called the KARNO Power Module. And as I was just mentioning, it's like a new form of power gen, a new way to make electricity. So fast forward a year later, we actually ended up acquiring that whole division out of GE, brought it under Hyliion. And then in 2023, we saw that the EV space was not heading in a good direction, right? There were a lot of our peers that were going bankrupt. It was tough to raise capital. The pace at which fleets were adopting new electric vehicles was slowing down. The costs were higher. The mandates were softening. So it was just this perfect storm that we decided, let's get out of the EV space and why don't we go all in on power gen? And that has been a fantastic decision as you look at the amount of power data centers need. The military itself, we're working on various different programs. They need a significant amount of power with unique attributes. And then just even commercial buildings. Like if you can provide a solution that someone can now make electricity cheaper than they can buy from the grid, why would you not do that?
Okay. So as you mentioned, 2022 was a kind of a key moment in the company's history, acquiring Carno from GE. Can you tell us exactly what you were acquiring at that time? How mature was that technology? And I guess what had GE developed up until that point in 2022?
So it was at a phase where prototypes had been made, but nothing that was ready for going to market commercial applications. So developing a new type of power generation technology, like envision going and developing a new turbine for a jet engine, right? Or imagine going and developing a new fuel cell. These type of endeavors take many, many years, if not in the order of magnitude of like a decade long to develop. The Carno is no different. So the team within GE actually started working on this in the 2017-ish sort of a time frame. And when we made the acquisition in 2022, it was at a phase where it had already gone through I think it was 3 different iterations of prototypes. And then when we made the acquisition, we even then brought it through another iteration or two, that then is now what we're bringing to market as our commercial product. So what it is it's a 200 kilowatt design system that's called a linear heat generator. We'll dive into this in a lot more detail, but the foundation is it actually uses heat as its fuel source in order to produce electricity. Now, how do we make heat? You can make it by reacting natural gas, diesel, hydrogen, propane, truly a variety of fuels that we can feed into our system, make heat, and then we'll be providing electricity through the power module.
Okay, so you mentioned there a couple of iterations since 2022 when you acquired the technology. So the commercial technology as it exists today, what would you say are the key capabilities of the technology? What does it enable? What does it allow your users to do?
So the general premise is you can now make your own electricity on site as opposed to being reliant on the grid. So if you think about a commercial building, most facilities have a big air conditioning unit either sitting on the roof or sitting outside to produce all the cold air for the building. Our vision is you do the same exact thing for power gen. You have a box that's sitting next to the air conditioning unit, and it's sitting there getting fed with whatever fuel you have available to you, and then it will produce all the electricity that that facility needs. And what this enables is for data centers where the grid doesn't have the capacity that data centers need, now they can move to on-site power generation and actually move faster than they could have before. If you look at a shopping mall, it enables them to now actually make their own electricity cheaper than buying grid electricity. And then if you look at applications like the military, we're the power plant on board the new unmanned military ship. So the nickname is the Ghost Ship. So there's no crew on board. It's this fully autonomous vessel. Well, if you don't have a crew on board, you don't have the ability to do maintenance on engines, right? So now what the Navy needed was a solution that was very low maintenance, could be deployed for months and months on end, potentially even years on end, with zero maintenance. And that's one attribute of our technology is it's inherently a very low maintenance solution.
I understand as well it's a scalable technology. So you mentioned that the first product you have is the KARNO 200 kilowatts power module, but I believe that you're looking ahead to kind of larger products. So talk to us about that kind of roadmap and the progress you're making there.
So the 200 kilowatt is perfect for, think of a Home Depot. One of those boxes could power an entire Home Depot. A Walmart supercenter, two of the 200 kilowatt boxes could power an entire supercenter. Now, reason that they need more power, they have all those fridges for the food in the facility, so that draws more power. But if you think about data centers, we're talking more in the order of magnitude of megawatts of power as opposed to kilowatts, or potentially even gigawatts of power. And so what we've also designed is a more modular system that is either 2.4 or 3.2 megawatts of power. So if you think about a 30 megawatt data center, they would deploy 10 of these 3.2 megawatt boxes roughly outside their facility, and that will produce all the power that they would need at that site. One unique thing though that I'm sure we'll discuss is inside that 3.2 megawatt box is actually just a series of these 200 kilowatt systems strung together. So 16 of them strung together in order to make that 3.2 megawatts. And then you string those 3.2 megawatt boxes together. So reason that we're doing that, we get asked this all the time, is why not just make a larger 4-shaft system that would make 3 megawatts itself? Well, the reality is that we've designed the system to really match the production machines, the additive manufacturing equipment, so that we're optimizing the size of these parts to fit on the print beds of these machines. And so if we make them just a millimeter bigger, now our production throughput is going to significantly take a step back.
So are you then constrained in terms of size of these systems by what AM can do as opposed to the challenge of scaling the technology into a larger form factor?
That's correct. So we've designed the parts to really match that 250 by 250 millimeter build plate size. And so our parts are 249 millimeters in diameter. And so that's where if we went bigger, now you're no longer able to use the M2 GE Calibrium machine, or we also use the M-line machine. It's a 500 by 500 millimeter build plate. We can fit 4 parts on that. If you go to the parts being a little bigger, and now you can only fit 3, then you can only fit 2, right? And that's where we looked at and we said, yeah, the real optimized size for additive manufacturing is this 250 millimeter. Let's just stick with that. And then as people need more power, you just string them together. And think of it like a battery pack in a car. You think of a Tesla, the whole floorboard is filled with thousands of these small little batteries that are all strung together. That's our same philosophy for power generation is you string a bunch of these Carno cores together at 200 kilowatt increments, and that gives you the power you need.
Yeah. So additive manufacturing, I assume when you acquired the Carno technology out of GE, that's kind of what they were doing. They were using AM for these power generation systems. Why is AM the kind of most suitable manufacturing method for these products? And I guess how important is AM to what you're doing here?
We don't have a technology if it's not for additive manufacturing. So that is how critical this is to our business. So if you think about our technology, it's based on Stirling engine tech, which is this concept that was designed, developed 200 years ago by, I think, Dr. Stirling. And he had this concept of if you trap a gas, so think of like a balloon, you fill a balloon with helium, right? Well, if you heat that balloon up, it would grow. Now, if you cool it down, it shrinks. Same thing with your car tires in the winter. Why do you need to put more air in them? It's because it got cold outside and it shrunk. So we do this heating and shrinking 20 times a second inside this chamber inside our engine. And that allows us, when it expands, to actually move a piston, and then that produces electricity, and then you shrink it back down, and it compresses the gas, and it pulls it back. And so that's how our system works, right? And that's a Stirling engine, been around for 200 years. No one has really brought this to market in a commercial application. Like organizations like NASA have used it for powering satellites, things like that. But it hasn't really been commercialized because it's been so difficult to manufacture. Specifically, it's so difficult to manufacture the heat exchangers that go into the Stirling engine. And so what we looked at, we said, all right, Stirlings have always, for 200 years, been kind of known as this euphoria of power generation. Well, there's been a massive breakthrough in manufacturing over the last couple of decades, thanks to 3D printing or additive manufacturing. Why don't we try to make those really complex heat exchangers with additive as opposed to conventional practices? And now that's enabled us to really unlock these euphoria benefits of a Stirling engine.
How do you approach the design of these systems? Has that been an in-house capability, or has that been a collaboration with third parties?
It's really been an in-house effort. So we have a rock star engineering team. It's led by our CTO, Josh Mook, who was one of the founders, really the founding member behind the Carno technology within GE. And then he had assembled a team around him at GE of brilliant aerospace engineers, additive manufacturing engineers. And then as we made that acquisition out of GE, that team came over as well. And so brilliant group, deep history in both additive as well as aerospace, and they've taken the reins within Hyliion to really go design all these components themselves. I would say we've got probably one of the strongest, obviously I'm very biased. I love our team, but we've got one of the strongest, if not the strongest, designers for additive manufacturing out there, and we're also able to then go push the bounds of what these machines are able to do, right? Because the engineer that's actually designing the components to go into our KARNO Power Module is also an engineer that has experience on how these machines work, and can really push the thought process as to what can be creative through additive.
Okay, so what would you say are the kind of big design drivers that make what you're doing the right method? What have been the design drivers prior to getting to the point where you're able to commercially launch? And I assume you look to advance the technology and advance what it can do. What are the design drivers now to innovate further?
Yeah. So the design drivers are making more and more efficient or effective heat exchangers. That's really the foundation of Stirlings in general is you have various heat exchangers within the engine, and you need those to operate at as high efficiency as possible. The more efficient they are, the more efficient the entire system is. So to give you an example of a couple of them, so there is a heat exchanger between where we react fuel and how you transfer that fuel into your, or I'm sorry, how you transfer that heat into your working gas. So I gave you that like balloon example with the helium inside. Well, our working gas inside the Carno is helium. So you're going to bring in natural gas, you're going to mix it with air, you're going to react it, you're going to make heat, and then you need a metal interface where you actually transfer that heat into that working gas, the helium. So the more efficient and effective that heat exchanger is, the more heat we can transfer through, the less heat that goes out the exhaust, all the above, right? So that makes it more efficient. The other one, which is kind of known as the most critical part inside a Stirling, is called the regenerator, which this is where you actually store heat in what we call our thermal battery. You actually store heat in it, and then as that you're heating up gas and cooling gas, heating gas, cooling gas, you're actually storing it in between each one of those cycles in this thermal battery. And that's a part that we've designed this extremely complex, intricate 3D printed mesh tubes that are our thermal batteries. Now, what happens is as that helium is flowing through that tube, it's actually heating up all those little pieces of metal mesh and storing the heat in them. And then as that helium comes back through it going the other direction, it's now able to pick that heat back up and reuse it again. So the regenerator is probably, I'd argue to say, the most important part within our system. And as we can continue to make that more and more efficient, then we'll get better performance out of our Carno.
Okay. I wanted to touch on the manufacturing workflow now. So a bit of context. I think you guys run 36 metal AM machines. I think more coming online in the future. So I think our audience will understand most of what goes on in a metal AM machine. But touch on that a little bit. What's going on inside the machine, and then what happens before that, if anything, after the design, and what happens in terms of post-processing once the parts are out of the machine.
Sure. So starting high level, as you mentioned, about 36 machines. We have the full suite of GE Calibrium printers, from the M2 to the X line to now the M line. Each one of them has a different form factor, a different number of lasers, but the nice thing is that across those machines, like, we can print one of our reactors on an M line, an X line, and an M2, right? So these machines are pretty universal on what they can print. And what's happening on the inside is, within the M2, we're printing one part at a time, one reactor at a time. On an X line, we'd be printing two at a time because it's got a longer build plate, and an M line will print four at a time. Now, as you know, an M2's got two lasers that then you're actually going around welding or melting the powder, the metal powder, and then you're going to stitch the two lasers together into your one part, versus on an X line has two lasers, but since we're making two parts, we just have one laser per part. And then same thing on an M line, you're making four parts, four lasers, so then you have four lasers per part. And we're really pushing the bounds of these machines. Like, we work extremely close with GE Additive, and they've expressed that those heat exchangers that I mentioned are probably the most complex things that have ever been printed on these additive machines. And we take a lot of pride in that, right? That last question you had, we talked about how the further we can push the boundaries of efficiency and how effective the heat exchanger is, the better our system performs. So if the additive machines are able to do it, then why not take advantage of it, right? And that's one of the really nice things or great things with additive is it doesn't really care whether it's printing a block of metal or it's printing an extremely complex part. It's just lasers going around that are, melting layer by layer and building up whatever structure you want. And it behooves you to just make as complex of parts that, obviously, if they have benefit, but make as complex of parts as possible, so that you can really push the boundaries of what's efficient, or what's efficient and what is possible.
Yeah. I think that leads nicely onto my next question, which is going to be about the business case. So the fact that you are running 36 machines sounds like there's a business case for additive here, and I appreciate when additive is enabling the application. The business case maybe takes care of itself a little bit. But what are the considerations you're making, or have been making, as you've been building this business case? What are the things you've been thinking about, and what are the things that AM has really kind of allowed you to do here?
I think it goes back to that foundational comment earlier of, we don't have a product if it wasn't for additive manufacturing. And to put numbers to that, so we're operating, targeting a 50% fuel to electric efficiency. Stirlings in the past that haven't used additive manufacturing, and our system would, one, it would be a lot larger, but two, it would probably only be in the 20s, maybe 30s percent efficient. And so, that's really the unlock is, let's just use round numbers. If you don't use additive, your KARNO Power Module is 25% efficient. If you do use additive, it's 50% efficient, right? So that means that because of additive, now we're going to use half as much fuel as we would have prior, right? So that's a huge benefit. That's a game changer, an unlock, right? And that's what end customers are looking at. They're looking at, what's my total cost of ownership, and what does it cost to operate this? What's the maintenance on the system? And so fuel is your number one expense in power generation, right? It way outweighs your initial capital investment that goes into the product. And so if you can make that generator more efficient over 2 years, 5 years, 10 years, that's going to be huge savings for the customer. And so, yes, additive is more expensive. Like, that is just reality. Casting is cheaper, but if it's enabling you to move from 25% to 50% efficiency in your product, now you can charge the customer more because you have that benefit. And then, ultimately they're going to see a lifetime ownership of the product that is much more favorable than if they were sitting there at 25% efficient.
Yeah. And do you find those conversations with customers where, okay, you're perhaps coming in with a more costly product, and you'd argue a more performant product? Do they understand that, and do they kind of accept that the higher the performance, the higher the cost?
They absolutely get it. And the cheapest way to go make electricity is go buy a emergency backup standby diesel engine. Like, think of sure, you have one at your house, or your friends have them, like you got standby generators or Generacs at your house, right? They're really just designed to kick on for a handful of hours a year and produce electricity and keep the lights on. They're extremely costly to maintain. They consume a lot of fuel, but they serve a purpose just to keep the lights on when it's needed, right? But they're also very inexpensive to go buy upfront and deploy them at a facility. The industry knows that, after a year, you'll be buying a new one or whatever. It won't take long. So the industry is well aware that, yeah, you can buy a very less expensive upfront solution, but in the long term, it's going to cost way more. Or you can go the other end of the spectrum of, you could buy nuclear, which costs multiple X's upfront of any of these other technologies like ours, and it's in a league of its own in terms of upfront capital costs. But operating cost is very low because there isn't, you're not feeding it natural gas or diesel, and so then that keeps the operating cost down. So, as I'm sure you've heard, I mean, the industry is very excited about nuclear as well, and yet that's probably the most expensive upfront solution you could buy, but yet it's still getting attention and people are excited by it. So I think the industry is well aware of its look at the operating it's called the LCOE, the levelized cost of electricity. Look at, what this is going to cost you over the lifetime as opposed to just on day one.
Back to the kind of scale you're operating at. So with installing and running 36 metal AM machines, you obviously need a business case, but you also need a very capable team, a lot of skill, a lot of expertise. So I wanted to ask you about how you've gone about building that. I appreciate some of that you'll have acquired from the Carno acquisition, obviously. But I guess the question is twofold. What in-house AM capability did you have before that acquisition, and then how has it grown since you've brought the technology into the company?
Yeah. So before the acquisition, we truly had zero, right? We had nothing in additive manufacturing. And once again, we were building electric semi trucks, and so it just wasn't our focus point. Through the acquisition, we had an amazing team come over of not only individuals who knew how to engineer and design components that could be printed by printers. We had individuals who had engineered the printers themselves. We had designed the printers themselves. We had individuals who knew how to do the maintenance on the machines, and then we also had individuals who knew how to flip machines and keep them running. And so that we kind of started with an unfair advantage, right? We got this brilliant team that came over and stood up that process. Now we've obviously had to scale that and grow it. So we've been successful at hiring people out of other machine manufacturers. We've been successful at finding individuals who have been at other companies who have used additive and been able to scale that way. The other thing we've been doing, though, is just finding individuals who are coming straight out of school and have an interest in additive. Maybe they at their universities were exposed to additive manufacturing and got to see it or work on a machine, and that's been a great fit as well. And then we've been able to bring those individuals in and really train them up on what our processes are. And as I'm sure your viewers know better than most, like you kind of create your secret sauces with additive manufacturing. So even to the point of, we've got this amazing and strong collaboration with GE. Well, we have our own little tweaks that we like to put on the machines when we're calibrating them, or, we want to do it our way because we found for whatever reason that's more effective with our parts. And so, so you got to kind of bring people in, teach them your secret sauce, and then continue to grow the organization around that.
Okay. You guys have obviously achieve success of AM, continue to invest in the technology, continue to scale. So we've established that it works for you, but what, if anything, could be improved upon, would help Hyliion do more with the technology? What, if you were talking to Calibrium, for example, what are the kind of things that you're demanding of them, that you're feeding back to them, that you guys want, that would really kind of help push things onto the next level?
Yeah, I'd say it comes down to speed and throughput of the machine, right? If we can take a build that maybe was a 5-day build and move it to a 4-day build or a 2-day build, right? I mean, that's a huge advantage to us because we're really trying to use additive at scale, right? Our manufacturing is additive. And so this isn't just make prototype number 1 through additive and then send it out to the casting house. No, if we're going to go scale this company as we intend to, we're going to need more and more additive printers. And if we can increase the throughput, whether that's through more lasers in the machine or parameter development or taller layer thicknesses or thicker layer thicknesses that enable you to just print faster, that's a huge win for us. That's why, I'm sure you've tracked the evolution of initially M2s were, and M lines as well, were 400-watt lasers in them. Now we're moving up to kilowatt lasers in them, and we're able to move faster. We already have our X lines running at kilowatt laser speeds, printing aluminum parts, and that was a huge speed improvement. So now we're trying to roll that into M lines, M2s as well. And then there's a horizon or a roadmap of ways that manufacturers like Calibrium are working on improving the throughput and speed of printing, and we're going to ride that wave, and we want to be a part of it because that's ultimately going to allow us to produce systems more cost effectively.
Mm-hmm. Finally, Thomas, and thank you for your time today. You've touched on this a little bit throughout the conversation, but in terms of the application of AM technology, how do you see it evolving moving forward? What do you see as kind of a realistic evolution of what you're doing and how you're applying AM?
Yeah. So our vision is in the years ahead in this facility that I'm sitting in, which is this big facility. It's a 120,000 square foot warehouse. My goal is we have in the order of magnitude of hundreds of machines lined up here, lights out manufacturing, right? Through the weekend, through the holiday, these machines are cranking out parts, producing components for our KARNO Power Modules. And as you know, we talked about just a second ago, we'll continue to keep pushing the boundaries of what additive manufacturing is able to do, the speed that it's able to make parts, and how many we can produce throughout the year, and continue to work with the producers like Calibrium on what's the next generation of machines, right? And be an early adopter of those and really push the bounds of what additive can deliver, because if it can deliver a more effective heat exchanger for our application, that's going to mean our customer has a more efficient product. That means that they're going to buy more systems and be happier with this technology, and on, right? So all this boils back to, though, we don't have a product if it wasn't for additive manufacturing. And so, we're huge cheerleaders of this industry, and huge adopters of machines as well, and look forward to be on the leading edge of what's possible through additive manufacturing.